In the previous videos, we covered several processes related to IoT Cloud and how devices are connected to the cloud. In the examples shown earlier, we manually entered the MQTT broker connection details directly into the ESP32 code. However, in a modern cloud, these details are actually hidden from the user. As an example, I'll present Arduino Cloud. When configuring the ESP32 or Arduino, you generate a device ID and a secret key, just like in our case. This is the final step in configuring your device. The user has to enter these credentials into the code, along with the Wi-Fi password, but they do not receive the actual MQTT credentials. If you look into the Arduino IoT Cloud library, you'll notice that the file Arduino IoT Cloud TCP contains the broker address, iot.arduino.cc, and, of course, the ports. So it does communicate via MQTT, but you won't find any hard-coded username or password. What you're seeing here is essentially a zero-touch provisioning mechanism, often used in modern IoT ecosystems to securely register devices with a cloud platform and allow them to communicate without repeated manual intervention. A zero-touch provisioning mechanism allows an IoT device to be configured, registered, and connected to a cloud service automatically once it is powered and connected to the internet, without the user needing to manually input authentication or configuration data. All cryptographic security and required settings are handled automatically by the system. This mechanism can be implemented in several ways. The device receives a certificate or cryptographic key during the registration process. Devices are added to the cloud using a device ID plus secret key. Automatic authentication. After registration, the device's credentials are used automatically for future connections. This process is handled by the code. Provisioning settings from the cloud. After authentication, the device can automatically download the necessary configuration settings. In the case of Arduino, the connection of the device to the cloud is handled through an additional application that needs to be installed. There is also a dedicated library for this purpose, and some more complex processes are involved. But in our case, we'll go for something simpler. There are several possible approaches, but we'll start with a very basic one and gradually improve it, adding various security features along the way. In this video, I'll show you a simple method. Let's create a device and associate it with a user. We now have a UUID and a secret key. These are the only credentials the device receives. At this point, the device has the status requested. In API PHP, we've defined a new route and a controller. This means that the first time the device powers on, it must make a POST request to this endpoint with the UUID and secret key. The Bootstrap function implements a provisioning mechanism for IoT devices, allowing a device to be automatically initialized without manual intervention. It validates the information sent by the device and, if correct, returns the data needed to connect to the central infrastructure, such as the MQTT broker. The request must contain two required fields: node UUID and secret key. These values are extracted from the request and prepared for validation. Device lookup. The system searches the database for a device matching the given node UUID. If no matching device is found, an error response with HTTP status code 404, not found, is returned, and a warning is logged. Authenticity check. The system checks if there is a valid association between the device, node_ID, and the secret_key. If this association does not exist, an error response with HTTP status code 403, forbidden, is returned, and the event is logged. Status update and credential generation. If the association exists and the device status is requested, unconfirmed, the status is updated to confirmed and saved in the database. If MQTT credentials have not yet been generated for the device, they are created automatically. A device-specific MQTT username, a dynamically generated password, MQTT broker details, host and port, retrieved from the application configuration. Final response to the device. If all checks pass, the device receives the necessary connection data. MQTT broker information, address, port, MQTT authentication credentials, username and password, A list of MQTT topics the device should use for publishing and subscribing to messages. How does it work in practice? We will simulate the process using Insomnia. We make a post request to this endpoint. We include the UUID and the secret key in the body. I intentionally used false data. The system will deliver the error. The node UUID field must be a valid UUID. Now, if I correct the data and send the request, and the data is found in the database, Laravel will deliver the broker's connection details. From here, it is simple. In the device code, the data can be saved in various ways to be used for subsequent communication processes. I will stop here and continue in the next video. Bye.